In bivariate analysis, we looked into quantitative to quantitative relationship, how to check quantitative to quantitative relationship, and the tool is correlation. Covariance actually can explain, but it gives you direction only, not the magnitude. When we took correlation, it is actually a normalized value of covariance. The terminology I'm actually talking, right? You need to remember this, and in interviews also you should be talking like this. Then they'll get they'll get a feeling that you're already working in the industry for last 3-4 years. Rather they'll get to know, this is all new stuff. So the covariance, normalized value of covariance is the correlation, and it'll have direction and magnitude both, because the range is between -1 and 1. Minus close to -1, too much negative relationship between two variables. Close to +1, no too strong positive correlation. Either one is expected. If the correlation is close to 0, we don't we don't want to use those features. And you can do a heat map and understand how the relationships are. But there is one caution we need to look into. Two cautions basically. One is correlation can explain only linear relationship. If the features are related like this, the correlation value is correct, whatever it is representing, right? If the data is having nonlinear, there is relationship, this can be used in our model. How we can use it? If I generate an equation like y is equal to x square, right? I can actually make predictions of the x, right? So of the y, right? So I can make predictions of the y. So there is relationship, but the correlation coefficient is unable to explain because the relationship is not linear. And then there are two ways, the two kinds of relations, correlation coefficient calculations. One is Pearson and second is Spearman. Pearson takes the actual values and tries to calculate correlation. Spearman takes the rank and tries to calculate. Especially when the scale of the features are different, Spearman gives you most appropriate value, because Spearman is bringing the data into same scale. If you take rank, when you are doing correlation, will we have the same number of features in both the columns, or different number of features, different number of values? I took two columns to calculate correlation. In first column 100, second column 20, second column 20 values. Can I take those two features and do correlation check? Can I do that?
No, I think.
Yeah, we cannot, right? We are taking the columns from the same data set, and we'll have same number of values in the column. So when you calculate rank, right, it will come to same scale. What is scale? Here and here both, right? They have 20 values. So most probably you will get 20 ranks, right? Most probably, because see this here 18.5, because the way we calculate rank is also differs, right? Sometimes all the values are same. I'm giving the same rank, and maybe giving the count and then taking an average and giving the same rank to all. So it'll almost come to the same scale. Okay, when the values are on same scale, the comparison becomes easy. Okay, so that is Spearman correlation. And yeah, correlation, the correlation is not causation. We have seen that, right? So firefighters and number of casualties not because of increase in firefighters, it is because of the area SFT. The area SFT is the actual confounding variable, which is affecting number of casualties. But when you look at statistical analysis, it looks like firefighters is also affecting the number of casualties. When we know business, we'll know which one is the actual confounding variable, and we should be building models using confounding variables rather than these kinds of misinterpreted variables. Or maybe that actually adds value, then you can use it also. So this is correlation. at a brief. And now we are going to look at chi-square test, another bivariate analysis. When two columns are categorical, when this can happen, two columns when they both can be categorical. When two columns can both be categorical, do you know? Where will we get this situation to see whether two categorical variables are related or not?
I think identify the fake news. News also categorization, right?
I was asking the question in terms of whether it is a regression problem or classification problem. In which situation? When we are actually trying to solve a classification problem or regression problem, where we will actually need to check the relationship between two categorical variables.
Classification.
Classification. Good,
yes.
Good. Right. So sometimes we may have to check relationship between input and input variable also, because if there is two strongly correlated, two strongly related input variables, right? You can eliminate one. Okay, instead of using 10 columns, right? You have 100 columns. Out of 100, 10 are strongly correlated. One correlation. Then you can take one column and remove rest all. I'll show one example. Once after we finish the statistical analysis, right? I'll show an example of. Okay, I'll show one example there, right? To end-to-end project execution example. Then you will get to know. Okay. So this is the chi-square test formula. Okay. The chi-square test of independence. We are actually looking at the chi-square test of independence. There are two chi-square tests. One is independence test, and the second one is goodness of fit. Okay. So I'll try to show. I think I'll try to show both. Maybe I'm showing this here. Maybe that example. Yeah, I am showing independence test only because we are trying to look at the relationship, right? So the null hypothesis is going to be the columns are independent, right? Columns are not dependent. They are not related. Same as in correlation test. In chi-square test is also the null hypothesis is going to be not related. And we need to get a p-value which is less than 0.05 to reject the null hypothesis, right? To say that the features are related, ultimately after calculating some math, we should get the p-value which is less than 0.05. Okay, so we'll see that. Chi-square test for independence is used to determine if there is a significant relationship between two nominal ordinal is a terminology. I'll talk about that. Nominal variables. Ordinal variables mean in categorical variables there are two kinds of variables. One is nominal, another is ordinal. When I say ordinal, right, there will be hierarchy, right? Like the quality of a house. Quality of a house is excellent, good, fair, and poor. Right? Four kinds of categories there. Those categories have got hierarchy, right? Excellent means high. Good means a little low. Fair means a little even lesser. Poor means not good. Right? So there is hierarchy. In some features, right, there will not be hierarchy. Okay, those kinds of features are called as nominal features. Okay, or categorical. For simplicity, we'll take it as categorical. I am explaining chi-square test for independence. I said that there is another test called as chi-square test for goodness of fit. Goodness of fit, we can use goodness of fit when now you are using some feature and trying to make prediction. How good the prediction is, to assess that we can use goodness of fit. That is not needed now, right? So when time comes, right, I'll explain. I took it out because it was actually a bit confusing when you look at both right at once. It was actually kind of a bit confusing, so I took it out. So maybe in later point in time I'll try to show that example again. Okay. Below formula calculates the chi-square test for independence. Right? This is actually called a statistic, that a number, a number that actually that can be used to calculate chi-square test for independence. So there are, if you look at this formula, this is not x, this is chi in Roman, Greek or Roman letters. Okay, they call it as chi, chi. Okay, the chi-square test, and there are observed values and expected values. So we are taking the observed values and the expected values. Right? Here, whatever the reality is called as observed values. Whatever the reality is called as observed values. If you look at this, I have taken that same, employee data, right? Designation and gender. Designation and gender both are categorical. Designation analyst, director, junior developer, manager, senior analyst. These are all categorical. Gender is also categorical. Okay. So if you look at category, this table, this is called as contingency table. Okay, this is called as contingency table. In pandas there is crosstab. No, there is a method called as crosstab which gives you contingency table. Cross tabulation we call it as. Okay, if you look at the gender, female analyst 2 in our company, right? There are 2 analysts who are female. There are 4 analysts who are male. There are zero directors. There are 2 directors who are male. Right? There are 2 developers. There are 0 number of junior developers, male junior developers, like that. Right? If you look at the total here, 14 and 18, how many female total, how many male in our company? If you look at these totals, right, they are how many analysts, how many directors, how many junior directors, how many. So this is a, when you have 2 categorical columns and you want to know the cross tabulation or contingency table, you actually use cross tab method and calculate. Okay, the problem we are trying to solve here is probability of gender having a designation with when null hypothesis is true. Here null gender and designation are independent. Okay, so what we are trying to say is gender and designation are dependent. Okay, what that means is gender and designation are dependent means what? There is a bias in the company, right? There is a bias. Now in the company, when they are giving job, they are looking at the gender and giving a job. See, I believe in this thing. When a person is capable, that person should be given a job, irrespective of gender and caste, creed, and whatever. Okay, so some organizations are actually trying to say like women empowerment and men empowerment. There is no empowerment as such. If you are powerful, right, you will get a job. Right? That's how it is. So is there a gender bias? That's what we are trying to see in this organization. Right? So my the statement of the person who is actually trying to find is there is gender bias. That's the statement. So null hypothesis is saying there is no gender bias. When I say gender and designation are independent, what that means? There is no gender bias. While giving job or while giving promotion, there is no gender bias. Okay. So do you understand the problem statement and what we need to solve? Any questions on the way I represented here or explain the thing? Any questions? Okay. So 2 categorical variables we are trying to understand relationship. In business perspective, what is the 2 categorical variables and understanding relationship? in business perspective, is there gender bias? That's what we are trying to see in the data. Right? This is for just data analysis you can use. This is just for data analysis. You take some data and you analyze and you find out whether there is gender bias or not. Okay, so to do that we'll use chi-square test because two columns are categorical and we are trying to understand relationship between them, whether the relationship is too strong or weak. What should be there? Gender bias should be there or should not be there in an organization?
Should not be there.
Should not be there means what should happen to the p-value?
Null hypothesis here we need to reject it. So p-value should be high. Less.
Should we
Sorry,
reject
less.
or accept?
So no, should be this should be rejected. So it should be less.
No. When I say independent, right? What that means?
Oh, sorry. Yeah. It should be high.
Independent. That's the it's not a big deal, but it's a confusing thing, right?
Yeah.
When I say gender and designation are independent, that's what I expect, right? The company should not have gender bias.
Yes.
Okay. So the company should not have gender bias. Okay, that's the expectation. So we should actually accept null hypothesis. If you want to create an organization that actually will not have gender bias, right, you should accept it. If not, right, you should reject it. So if in my view, if we accept, right, that means that is good. Or we are not favoring male, that's another thing. If these two are independent, that means the company is not favoring male, even though it looks like two directors are male. No directors are there. Female directors, no female directors. Two junior developers are there and no junior developers male are there. It looks like high positions are occupied by male and low positions are occupied by female. Right? Even though the data looks like that, do we have the bias or not? That's what we are actually trying to analyze. To do that, we need to use this formula and calculate statistic. After calculating statistic, we need to look into a statistical table and do that final conclusion. Okay, so observed values and expected values. What are observed values? The reality. How many analysts are there who are belonging to female? How many analysts are there who are belonging to all these numbers which we got from data set are observed values. We need to calculate expected values. We'll calculate expected values using probability. Okay, today I am going to get into a little bit of probability, right? So the way I design the course is visualization and probability. I'll induce into other concepts and try to explain. Okay, they are not separate classes and separate. It's going to be boring if I try to explain separately. Okay, so we need to calculate these values using R, right? R rows and columns I said, right? So what is rows and columns here in this contingency table, right? In this contingency table, how should we actually take these values? Row 1, right? This is like two for loops, for loop within a for loop. Observed value, right? Observed value of first row I have taken, and then first column, second column, third column, fourth column, fifth column, sixth column, right? All observed values I will put it here. Expected values will also have the same structure, right? What I'm expecting in a company to have theoretically what I'm expecting to company to have in an analyst place for female, in an analyst place for male, in a director place for female, all these values, how would I expect theoretically? That is expected value. How to calculate that? Using probability. Let us look at it. So how to calculate expected values? The probability of a gender having a designation when null hypothesis is true. Okay. The expected values are calculated when null hypothesis is true. Right? Even in the other example, right, rat example also, we were calculating the null hypothesis. We were calculating the probability or the z-score of the value when null hypothesis is true, right? That is expected value. There also it is expected value. Theoretically or historically, what are the values here? kind of thing, right? So probability of gender having designation when null hypothesis is true. What is null hypothesis? Gender and designation are independent. That is the null hypothesis. Based on this null hypothesis, right, we need to calculate probabilities. Let us calculate it. So when gender and designation are independent, probability of gender G and designation D. G can be male or female. Designation D can be one of the values, analyst or director or junior developer. So these are variables, random variables I have taken. Okay, G and D are random variables which will take one of these values at a given point in time while calculating the probability. For one record, for one record belonging to G and D, right? Probability of gender is equal to G and into probability of designation is equal to calculate this probability. You can calculate it like this, because gender and designation are independent. When two values are independent, this combined probability is equal to multiplied probability. That's the probability formula. Okay. Any questions, confusions there? When you have to calculate probability of gender and a designation, it is equivalent to probability of gender into designation. Okay, because gender and designation are independent. This is a formula in probability. No questions, right? Clear, right? Till here? Clear, confused? So for one record, you need to calculate like this. For all records, right, you need to take the total count and multiply the original probability, where gender G belongs to M and F, designation belongs to all the other. So this is like, this is like mathematical, representation, right? So I am trying to induce a little bit of mathematical representation also, because in future you may have to look into mathematical formulas for new algorithms. Okay. So let us calculate probability of gender male and designation junior developer. We'll get more clarity if we do this. Because gender and designation are independent, we can calculate probability of gender is equal to male and probability of designation is equal to junior developer individually, and multiply them. You get the total probability, the combined probability. Okay. So gender is equal to male. What is the probability? How many male are there? 18 out of total 32 employees. Right? This is the male probability. The female probability in the organization, sorry, female probability is going to be 14 by 32, but we no need of that. Probability of designation in junior developer. How many junior developers are there? Total 2, right? Out of 32 employees. Okay, this is the total probability of gender is equal to male and designation is equal to junior developer. Did you get it? Is this simple? Is this ratio? Are these numbers ratios or something else? Any questions?
It's ratios only.
It's ratios only, right? So probability is nothing but ratio. Okay, the bottom line is ratio, but the formulas actually kind of multiply and divide and all that. So they are simple. So probability of gender male and designation junior developer for all records. Total number. This is for one record. This is for one record. One person becoming, sorry, one person male and being a junior developer. What is the probability? Okay. One person being female and being junior developer. What is the value? One person being female and being a junior developer. What is the probability?
14 by 32
14 by 32.
into 2 by 32.
14 by 32 into 2 by 32, right? So that is for one person. For all people, right? For all people, we need to calculate probability. For if you take 32 people, out of 32 people, how much percentage? How many people are going to be junior developers? Out of 32 people, how many are going to be junior developers and male? It is 1.125. Similarly, we can calculate for female also. Using these formulas, right? Using this formula, I calculated probability for all the records. So if you look at these numbers, right? These numbers, Out of 32 employees, how many are female analysts? Out of 32 employees, how many male analysts? So we need to calculate probabilities also, expected values also. Out of total 32 employees, how many are female analysts? Out of 32 employees, how many male analysts? Like that, okay? So we calculated these values using this kind of formula. So I'm actually trying to show you how a statistician does chi-square test. The formula is this. We need to have observed values and expected values. The observed values are from the data, the counts from the data, and the expected values are the values, are the probabilities where null hypothesis is true, right? In theory, what we expect is null hypothesis is true. When null hypothesis is true, in that situation, what are the probabilities, right? Theoretically, probabilities are the values, right? So we took that. Theoretically, null hypothesis says that they are independent. It made our life easy in calculating the probabilities. If they are dependent, right, we may have to do conditional probability. Male being a junior developer, female being junior developer, all that is going to be a bit complex. But this independence assumption, right, it actually gave us a little, not assumption, null hypothesis situation gave us more flexibility. We calculated the expected value table also. Dimensions of expected value and the observed value are same, right? Right. This is actually, if you look at only the values, it is 2 by 1, 2, 3, 4, 5, 6, right? 2 by 6, right? That area only I am looking at. Okay. And then here also it is 2 by 6. So now you can actually do I is equal to 1 to R and I is equal to 1 to C, right? Because rows are going to be, and rows and columns are going to be same. We can actually calculate those values like this. Chi-square test is equal to, right? First value is 2 minus observed value minus expected value whole square divided by observed expected value. Sorry, I forgot the formula. Expected value. Again, second one 0 minus 0.87 divided by, like that we calculated chi-square value, right? Chi-square value for the columns F1 and F, sorry, designation and gender. We calculated the chi-square value. Now to know the critical value, we call it as at a p-value 0.05, we need to find out, right, we calculate the chi-square value, right? This chi-square value fall into some area. We need to see where it is falling. Okay, so to know that, right, we need one more value which is called as degrees of freedom. I don't know whether I explained degrees of freedom or not, but let me explain that. So this terminology is used in AI, so we need to understand. So let me try to explain degrees of freedom, right? If I have, right, I have one value here, right, 10, and another value here, and another value is like maybe 8. Okay, so if I know that this is x1, this is x2, and this is y. If I know a formula, right, x1 plus x2 is equal to y. Okay, can I find out x2 here? If I have values like this, can I find out x2?
Yes.
Yes.
This is called as degrees of freedom 1, right? How many values are, when how many values are missing in the data, you can find, that is degrees of freedom. Okay, so one value, even if one value is missing, we can find. Two values we cannot find. So in this particular kind of data set, 1 is the degrees of freedom. But in this kind of data set, right? In this kind of data, there is a degrees of freedom. Like, if I take, maybe I generally take another example, but yeah. So let me take another table like this, simple table. Okay, so now I have values here, right? Value here as 10, 12, and then 8, maybe, and, 6, maybe 7. But if I have values like this, right? Even if these two values are missing, I can find out, right? Degrees of freedom increased because of having row wise sum and column wise sum both, right? Do you agree? If I put 4 here, it actually satisfies 10. This 11 also satisfies. If I put 4 here, not 4. 4 plus 7 is 11, right? 4 plus 7, maybe I should put maybe 5. And then here also I'll get 11. Right. So if I don't know these two values, I can find out because row wise sum and column wise sum both are there. So to calculate degrees of freedom, right? Generally, when you have row wise sum and column wise sum, you use this formula. If we have only one directional data, right? It is r minus 1 only. If you have two directional, then it's going to be r minus 1 into c minus 1. Right? This degrees of freedom is going to be how many rows? 2, right? 2 minus 1 into 2 minus 1. No, I think 2 and 7 right here. 2 minus 1 into 2 minus 1 is only one value. It's saying one value, but we can find 2, right? One, 2, 3, 4, 5, 6, 7. Yeah, even if 6 values are missing in this, right, we can find because the totals are there. That is the theory there. But here, right, when you look at it, even if 2 values are missing, we can find it. Is that right? Any 2 values missing, we can find, right? But when you use formula, it is 2 minus 1 into 2 minus 1 is going to be 1. The degrees of freedom, it is saying only 1. That's okay. That's okay. So degrees of freedom formula is this one. On this kind of data, it is row minus 1, and on this kind of data, it is row minus 1 into column minus 1. I forgot the. I think can we find 2 values or 1 value? That's the. That's okay. It's okay. We'll see that later. No, I'll come to that later, right? I'll think about it today. The degrees of freedom formula, actual concept is that one. How many values are missing, you can find, right? When how many values you can find when even when they are missing. That is the degrees of freedom. So we need to have degrees of freedom and the chi-square statistic value to find out whether to reject or accept the null hypothesis. The critical value for chi-square statistic is determined by the level of significance. Generally, what we are doing, we are calculating the p-value, right? In our previous correlation example or rat example, what we did, we actually calculated the z-score, and then we calculated p-value. Using p-value, we actually said whether to reject or accept. But in chi-square test and ANOVA test, it's going to be a bit different. Okay, at significance level, there will be a critical value. We'll see whether the chi-square value calculated, the chi-square value calculated is less than a critical value or the greater than critical value. Based on that, we accept or reject the null hypothesis. Okay. So if the observed chi-square test statistic is greater than critical value, then we reject the null hypothesis. If it is less than, right, we accept the null hypothesis. So there is table, chi-square statistic table. We have seen the z-score table, right, in our apples example. Like that, there will be chi-square table and ANOVA table also. When you look at chi-square table, there will be for different significance levels, there will be critical value. Our chi-square value is less than the critical value at the degrees of freedom, 6 degrees of freedom. So we have to accept the null hypothesis. That means gender and designation are independent. There is no bias in this particular company. The data that is belonging to this company, there is no bias. Did you get the total gist? You know, I actually crumpled a little bit here in the degrees of freedom, but the concept is right. Okay. How many values, even when they are missing, you can find in the data is the degrees of freedom. Okay. But rest of the concept, did you get it? How exactly we calculated, you know, the chi-square value, and then how did we do the statistical test, whether to reject or accept null hypothesis? Any questions there? Any questions? No? Shall we move on?
Yes, sir.
Okay. So I'll show code example, right? These are all things I did not do manually. Every time I am trying to explain you this. You need to understand the concept. To do all this, we have tools. Let me show you that. Okay, I have taken employee data. Let me execute this. Okay, so we have all these columns there, right? We already know. And I took gender and designation and trying to see whether gender bias is there in this company or not. Okay, so I looked into the head. I took only those two columns and created. I don't need this. You know, LOC. If I say, okay, I need it. I think if I don't use that colon, right, it's not going to work. Do you know what that colon is?
All rows.
All rows, right? See that when I am using LOC, I should be using that. If I don't use LOC, right? If I do like that, right, it will come. Okay, but still I am using LOC. Why? Do you know why?
Remove the index, sir.
Sorry.
Index, this one index.
No, even when you do like this also, it gets an index only, right? But the problem is going to be when you are trying to apply operations, right? It will say you are trying to apply operations on a slice. Try to do that, you know, try to take out this and take out this and execute the code and see somewhere down below. If you are trying to do some operations, these lambda, you know, these lambda operations and all that, right? It will say you are trying to apply changes on a slice of the data frame, and it will throw warning. You know, it will show warning. Okay, so when you are actually trying to take a cut of the data set and try to do some more manipulations independently of the original one, you should do like this only. LOC you should definitely use. Okay, you should use LOC definitely. That's where I used it. Try to do this experimentation instead of taking LOC. Just take the slice of the data frame and try to work with it, and you will see the warnings. Okay. So I took the slice, all rows I want, and these two columns only. Okay, I have got the whatever, right? and then I'm looking into the unique values of gender and designation. Okay, before I do analysis, right, I may do some visualization, right, and try to understand whether the data is really independent or not. What is the question we are trying to answer? Whether this company has got gender bias or not. Okay, let's try to understand the support for women in the organization. Right, we are actually trying to see whether the company is actually trying to place the men in the higher designations and women in the lower designation. When we looked into the data, right, we have seen that. Right, if you look at this, directors are all male and junior developers are all female. It looks like the company is not doing right. Right? There is gender bias. It looks like. Right? So let us try to understand the support for women in this organization. Okay, and then to do that, right, how much percentage of women are present in higher management roles? That's the question we are trying to answer. Or is it really right? So in the visualization, we'll actually see how many are there in the higher roles. Need to draw a bar graph between gender and designation. Do you see problem here? I'm saying a bar graph between gender and designation. Till now, did we do anything, any such thing? A bar graph between two categorical columns. Did we do this before?
No, I think.
No, right? When I say bar graph, always what I said? Even if you don't understand chi-square test, that's fine. But this one
It's
you
a discrete values, countable values.
Yeah, countable values on x-axis and y-axis. Counts of those discrete values, right? Gender and designation, if you take an x-axis, how many, right? Sorry, male and female on x-axis. Generally, what we were doing, we were taking either gender or designation and trying to do a bar graph. Got it? Let me try to show that here. Yeah. Okay, those graphs are not here. So generally what we are doing with the bar graph, this is the kind of thought process you should have. When I am trying to explain something, right, you should not just listen, you should question why this guy is doing this, right? So maybe bar I can do directly. So series of the value counts. See that? On an individual column, on one column, we are actually doing bar graph. But what I'm saying here, we are going to do a bar graph between gender and designation. Is that possible? Is it possible? It is possible. You'll see that. How? Okay. So, right, different designations on y-axis counts, right? Probability or count, it doesn't matter. Okay. So this is the bar graph. Generally, this is the bar graph. But now to understand relationship between two categorical columns, we are actually going to do a bar graph between two categorical columns. This is very important. In real time, you will do these bar graphs many times. Okay. So need to draw a bar graph between gender and designation. First, we need to answer two questions. When you are trying to do a bar graph between two categorical columns, you need to answer two questions here, or no, three questions I kept here, right? What is the type of explanatory variable? What is the type of response variable? If you look at this designation and gender, right? Designation and gender, and if you look at the data set, are these two independent variables or dependent variables? Any dependent variable there?
No, independent.
Both are independent variables, right? Gender and designation. When we are building model, right, we are actually trying to predict salary using all the rest of the features. That point you need to remember. Okay. Gender and designation belong to independent variable. I used new terminology here. Explanatory variable and response variable. What is response variable?
Targeted one. Designation.
Target variable. Salary is the response variable, right? If you look at the whole data, salary is the target variable. But for this particular scenario, right, is there, support for women in the organization, or gender bias is there in the organization? Which one is target variable and which one is independent variable? For this particular analysis, data analysis we are doing. For this particular data analysis, is gender the target variable or designation the target variable?
Designation.
Designation is the target variable, right? Based on gender, is the organization deciding the designation? Based on gender, is the organization deciding the designation? So designation is the target variable. Gender is based on input. We are deciding the target variable, right? So then gender is the input variable. So whenever you are doing an analysis between two categorical columns, you need to understand based on what the other one is getting decided. Okay, so if you have that clarity, right, you can decide that gender is the explanatory variable and response variable is the designation. Okay, so we answered that question. If response variable is categorical, find out how many categories are there in that response variable. Okay, so the response variable is categorical. Find how many categories are there. Only 2 categories are there. What response variable? If response variable is categorical, find out how many categories are in it. Only 2 categories should be present in the response variable. Okay, that's correct. So only 2 categorical variables should be present in. If not, right, we should be collapsing it. What is collapsing? We try to make the total number of designations to 2 categories. Managers and above 1 category and below all are 1 category. Because what are we trying to analyze here? How much percentage of women present in higher managerial roles? That's the disparity we are seeing here, right? When you look at the data, the disparity we are seeing is directors are male, junior developers are female, right? All directors are male and all junior developers are female, right? So we are trying to see that whether that is true or not, right? So that's where all higher management I gave a category number 1. All lower management I gave below non-management role I gave 0. Okay, so to actually do a bar graph between 2 categorical columns, the condition is that a target variable should have only 2 categories. But in here, in this particular situation, designation has got 7 categories. So we are actually collapsing them into 2 categories. What is collapsing? Grouping. Okay, managers are all 1 and all non-managers are all 0. Right? NGO. I think non-gazetted officer, right? Gazetted officers, right? Whatever, right? So this part, collapsing part is clear, right?
Yes.
Okay.
Yes.
So I'm going to do that. How to do that? I wrote some code here. Okay. So I looked into the data type, whether they are categorical or not, and I looked into the different categories there. There are 7. So I need to collapse it. To collapse it, I actually built a method here. Map designation to binary. What's binary? 0 or 1. Okay. So I am taking the designations, designations, and if the designations are present in this, if the designation is present in these 4, right? I am returning 1. If not, I am returning 0. Okay, this is simple method, right? It's simple, right? And this list of designations I have taken here. So on the data, on the series object, right? I have taken the designation, and on the series object there is a method called as apply, which takes a lambda function as input. Okay, lambda function as the parameter. In the lambda function I passed x. What is x? On this series object, If you say apply and lambda function, if you say x, what x will get?
Each item.
Right, each row, right? Each row, what the designation it is getting. And in the map designation, I'm taking the designation. If designation is present in this, I'm sending 1 back. If the designation is not present, I'm sending 0. Right? So I actually converted designation to designation binary. I'm adding a new column in this particular data frame, which will have zeros and ones. Right? There are 20 management role people and 12 development roles. Right? Got it? I collapsed the data using apply method and a lambda function. Right? Any questions there? This is data pre-processing. To do our analysis, we did some data pre-processing. Okay. Now I can do the bar chart. Okay. Bar height shows the percentage of ones in each category. Okay. It seems women in manager roles are less compared to men. Right. Let us look at the graph first, and then we'll understand the statement. So if you look at this, I used cat plot from CBAR, which actually takes the data and the gender it takes and the designation it takes, and kind is bar. Okay. So CI is I think color. I think I forgot. We'll see that in a moment. In the API we can see that. X label, Y label. When you do categorical plot and pass the two categorical columns and say bar chart, right? It is going to take the generally what this is actually numerical only. We converted the categorical column into numbers, right? One column into numbers. So it is going to show you the percentage of category 1. Okay, male category managers percentage it is showing. Female managers percentage. The height of the bar is going to show you the managers percentage. Because our goal is to know, our goal is to see how many managers are male and how many managers female in the organization, right? Did you get the graph? Did you get the graph? Any questions?
So on the y-axis, it is showing us, 0.1, 0.2 to 0.7.
That is what? That's the question.
Yeah.
Percentage of managers. The point he said here, right? Bar height shows the percentage of ones in each category. Okay, male or female. We have taken input variable as male or female, right? X is male or female. Y is designation. But we collapse designation to 1 and 0, right? So the bar height is going to show you how many ones are there in male, how many ones are there in female. Right, out of 100. This percentage of ones. How many managers? Right, out of total male, almost 68% are managers. Out of total female, 58% are managers. Got it? Got it? No? Yes?
No, the representation is a bit confusing, right? 0.6 is, so when you say 68, it is 0.68.
Yeah,
Just below the
0.68 is
0.7.
68% it is.
Okay.
0.6 is 100, 60 by 100 is 0.6, right?
Yeah, understood, but the representation got a bit confused.
Representation,
Is it automatically taken like 0.0?
automatically it takes.
Mhm.
I didn't get your confusion. I was trying to answer the question, but anybody else has got any questions? Maybe that answer may answer your question. Give me 1 second. Did you guys get it? Any questions here? Can I move on?
Yeah, Rama. Here, see, if it is taking y-axis as a percentage, then like what is it? Some of the axes also like should be matched with y-axis, right? For example, male and female percentage should be 100. Right?
No, not that. Yeah, maybe Shashiram's question is also the same thing. No, not that one. Out of, it actually divided male and female to two parts, 0 and 1 in the data, right? There may be 100 male and 100 female. Out of 100, how many are managers? Out of 100, how many are managers?
Okay, the both are separate. Okay.
It's separated. That's what we did in the collapsing stuff, right? We did that. See, bar height shows the percentage of ones in each category, male and female.
Okay.
Got it, Shashiram? Is that your question?
On the similar lines, yes.
Right? Yeah. This is a bit confusing. This bar graph is a bit confusing because it's between two categorical variables, right? It is not going to be that clear like a numerical one. And so far, right, we were actually looking into univariate analysis and univariate bar graphs, or visualization. This is first time we are looking into maybe the correlation is also bivariate. On a two categorical columns, right? This is first time we are looking at. So you need to look at male and female separately. What is the analysis we are trying to see? How many male are managers and how many female are managers, right? Out of total male, right? When you are trying to say that, I made a statement. This company is favoring male in giving managerial roles, right? Then what you should look at the bar, right? Out of total male, how many are managers? Out of total female, how many are managers? Then compare both and see, right? It looks like the female are given less responsibilities, managerial responsibilities. Male are given more managerial responsibilities. Right? Out of 100 male, 68% are managers. Out of 100 male in the organization, 58 are managers. Got it? On average. Got it?
Yeah, yes, but I think we have taken the senior analyst as a manager. Is it correct?
Yeah. This is for explanation. You can play it. Okay, so if you want to do non-managers percentage, right? If you want to see visually non-managers percentage, you need to give 1 to the non-managers, 0 to managers. I just flipped it, right? I did managers graph, bar graph. Now non-managers bar graph I wanted to see, right? Two categorical columns and try to. So if you flip it and do the Seaborn cat plot, right? You get that. Okay, this is a whichever category gets 1, that category is percentage it will show. Okay, that point you need to remember. Okay, so when I looked at visualization, it looks like there is a bias in the organization, but visualization may not give you clarity because visualization just looks into the current data. When you do hypothesis testing, right, it actually does, the large scale sampling and then, taking means, that whatever central limit theorem kind of a stuff it will do. Then you will get to understand how the population is behaving. Got it? When you look at this, it looks like gender bias is there. Do you agree?
Yeah, a little bit.
Little bit gender bias, 10%, gender bias is there. It looks like that. But especially when you visualize the gap between the percentages is very less, there may be a chance that our understanding is wrong. In that case, you may have to do inferential statistical test. In real time, how many times I did? Never. In real time, in my experience, maybe once, maybe in IRA project only once I did it, but generally we will not go that deep into statistics. Okay, the hypothesis testing depth will not go. So by looking at this, I see that there is some gender bias, but I wanted to make sure whether that is really true or not. My understanding after looking at the graphs, is correct or not. To make sure, I'll use hypothesis testing. Okay, so we'll do chi-square test to see whether the null hypothesis is true or the understanding by looking at the graph is true or not. So can we use gender to predict designation, right? When there are gender bias, right, we can use gender to predict designation. Do you agree? When there is gender bias, we can use gender to predict designation. My statement is I can use gender to predict designation. If he's a male, I can say manager. If he's a female, sorry, she is a female, I can say a non-manager. Can I do that? If gender and designation are biased, right, are strongly related, or there is gender bias in the organization, can I use gender to predict designation? Yes. No? Right?
No.
So I wanted to
Yes.
see that. Our main goal is different, right? We wanted to see that and this also, right? As an analyst, I wanted to see in different directions, right? Thought process, right? You need to change your way of thinking. Generally, when we are developers, right, we get requirement, we just code it and dump it on the face of the client. But that's not the way we have to do here. They'll give you data. Sometimes they'll not even give you data. You may have to collect the data also. Data engineering part also you may have to do. There are some cases where you will not have data. You need to create data. We were actually doing that with one of our client NTPC. I'll show you that example when we actually look into deep learning. I'll show those projects, right? So I'll show what we did in those projects and all that. So we need to collect data and all that. You never should be complaining in data science job because the industry is settling now. You will not have everything ready. That mindset also we need to develop. Okay, can we use a gender and a designation, right? Can we use gender to predict designation? So chi-square test will give you chi-square test for independence. Now there are two, goodness of fit and independence. So I'm using independence test to check that. So null hypothesis is the gender of an employee and designation are independent. That means there is no bias. Alternate hypothesis, they are dependent, there is bias. Okay, so to do the chi-square test, I need contingency table. We call this as contingency table. To do that, we need to use crosstab. Okay, this crosstab table is useful many places when you are trying to analyze pivot table, they call it as. Okay, do you know pivot table? Have you ever heard about it?
Yes, sir.
Yes.
Okay, so the pivot table. Okay. So try to look at what is pivot table. Okay, so same way, right? This is also pivot table or contingency table or crosstab. Okay, I took gender and designation and I margin through like I wanted to have the line or not. So this is same thing I copy pasted in this slide. Okay, I never did manual calculation. I just did the coding here, took these things and kept it in the slide. Okay, and the chi-square contingency is a method which actually takes the contingency table, right? Chi-square contingency from stats. What is stats? SciPy stats, I think. Yeah, SciPy stats method has got stats. SciPy is all about statistics. NumPy is all about linear algebra. Okay, so chi2 contingency will take contingency table and correlation is equal to false. I said I need to look into this. I forgot what that is. Maybe by default it is. So the chi-square contingency is taking this table and calculating the expected values also. How is it doing it?
Probability.
Yeah, probabilities, right? To calculate these probabilities, you need this table. This table I am passing it here. So chi-square contingency needs a contingency table. Why? Because you need to calculate expected values. Expected values need probabilities. The numbers needed to calculate those ratios. Probability is nothing, ratios. Okay. If you know probability is a ratio, that is enough for machine learning and deep learning and NLP and all that. Okay. No need to know in-depth probability. I may show you some, in-depth here and there, but even if you don't know it, it is okay. Probability is just the ratio. To calculate those ratios, it needs this contingency table. This method needs this contingency table. So that's where we are passing that, and we got expected values using expected values and the the table, right? The chi-square test, the chi-square statistic table, critical value and all that, right? It will calculate the p-value, or it will actually calculate p-value also. In null hypothesis scenario, it may do many times, and I don't know how it does this p-value calculation, but by looking at the p-value, it is actually greater than 0.05. You can reject it. Or chi-square value also it will give. See this? This method is returning multiple values. Do you know Python in Python method can return multiple values? Python function, if you write a function in Python, it can return multiple values. Do you know that?
Yes, it can.
Right. So here it is returning 4 values: 1, 2, 3, 4. It is returning degrees of freedom. It is returning expected values table. It is returning p-value. It is returning chi-square value. See this chi-square value, p-value, expected value. I did not print degrees of freedom. I think maybe it is 6 or 5. I don't know. So let me try to execute this. Rama also. Degrees of freedom. So 14. 1, 2, 3. 1, 2, 3, 4, 5, 8. I think it is taking the counts also into consideration. Let me see. 8 minus 1 into 3 minus 1. Yeah, it is actually taking the counts also into consideration. I think I should change this slide here. Right? So that's where I was getting a problem. Here now it is 3 minus 8. It is taking this row and this column also into consideration. When I showed you the example, right, there it is like 3 minus 1 into 3 minus 1. It is actually 4 is the degrees of freedom. Yeah. So I need to change this. Okay. So degrees of freedom is 14. So p-value is greater than 0.05. So we accepted null hypothesis. Right. So if it is less than, right, we would have rejected null hypothesis. So there is no gender bias in the organization. Gender and designation are independent, and then you cannot use the gender to predict the designation, or there is no bias in the organization. The organization is good. You can work there. Got it? So we are doing data analysis. Parallelly, we are trying to understand how can you use the data analysis in machine learning, or while building models in feature selection, how can you use? Got it? Any questions?
Rama, I have small confusion. See, Python is returning the multiple values, right? Just now you said like X table, df, p value. This value, 31, line number 31. Do you need to follow any order here?
Yes, sir. You need to look into this API. And the same order you need to follow.
Okay.
If you look at the API, it will actually show you that chi-square, p, freedom, and expected.
Okay.
Right? When you look at the source, right, you will understand more clearly what is it doing.
Oh.
See this? Return order. I got to know like that. I just copy pasted this here. See that? I think I kept underscore something, but that's a good question. So even when you write some code, right, when you are passing multiple values, you need to follow the order. If these values are not needed to you, you should put like this underscore. I don't care what that is. I don't care what that is. Right? Only I want expected table, so you should put underscores there. You will find that kind of a code in internet when you are trying to look for examples, right? You will see That kind of.
Okay.
So any other questions? I'll stop here today.